So what will I cover in this presentation? First, I will talk about contrast versus ANOVA F-test briefly. Then I will work with simulated data. First, with just 2-factor levels, I will introduce the mixed design function, which we will use to simulate data in this session. And then, as I said, a very basic introduction to contrasts examples. I will show a visual overview of how you can define contrasts, what contrast coefficients you can use. We'll show how R codes contrasts as covariates, or how you can do that manually, and look at different types of contrasts that are out there. And then I will switch to an example with 4-factor levels and just show what kinds of different contrasts one can use to code a 4-factor level. And this will show you that the contrasts really define what your model is estimating. If you don't know what the contrasts are, in many cases you have no clue what the significance of the coefficient means. So this is really key. So contrast versus ANOVA F-test. So in factorial experiments, where you have factors, different groups that you compare with each other, the standard that has been used in the last years, been used for many years, is ANOVA, analysis of variance, the omnibus F-test, where you just test whether a factor is significant or not overall. However, if the factor has more than 2 levels, this omnibus F-test is not very informative. So you don't really know where the effect comes from. And that's a bit unfortunate, because typically, at least in my field, but in many fields, I think researchers have very specific hypotheses about which conditions they expect to differ from each other and which conditions they don't expect to differ from each other. So this is the case I'm going to talk about. What I'm going to assume here, that normally we have very clear idea about how these condition means should differ from each other or should not differ from each other. So in such a situation, we can use a priori contrasts. So these are comparisons that are planned before the data are known, or the data is known. So this is an appropriate way to represent scientific hypotheses in the statistical model. And the argument is that a priori contrasts yield far more precise confirmatory tests of experimental hypotheses than the standard omnibus F-test that is often used. Indeed, this view has been proposed by Hayes in 1973. He said contrast should be tested instead of, rather than as a supplement to the ordinary omnibus F-test. And linear mixed effect models make it easy to switch to this perspective, because you have to code contrast when you fit the model. So there's no way around that. So the question then is, of course, how do we code our hypothesis into a specific contrast? So if we do have some hypotheses, we want to have contrasts that test these hypotheses. So how do we do that? And I will present different approaches to this question in the sessions today. The first and standard approach that is often used is that people just use one of several different standard contrasts. So there are standard contrasts that are known to implement certain hypothesis tests. And I will walk you through the different standard contrasts that are out there, not all of them, but a good set of them. And the procedure would then be that if you have a given study, you can think about a standard contrast that best tests your hypothesis, and then you use this contrast. Later on, in the later session, I will also show you how you can define hypotheses, write down your hypotheses, and then automatically obtain a contrast matrix that tests these hypotheses. So this is a bit superior approach, because you are very flexible here. You can just define the hypothesis that you want, and then you get the contrast matrix for it. But the standard approach is really different. The standard approach is that you have one of these set of contrasts, standard contrasts, and you use one of them. So we have, because they are very prominent and very important, I will discuss these here. So we'll use a bit of tidyverse, but not much, mainly ggplot. So I will first start with a very simple example, and note that in this very simple example, contrast coding might not be really important. So I'm not discussing that here because in this situation that we discuss, contrast coding is important, but just to show you how the contrasts work. So I will start with a situation where we have one factor with two levels, most simple factorial design, just two groups, x1 and x2. We assume that the condition means so the condition means are just the mean of the dependent variable in group x1 and the mean of the dependent variable of x2 are 0.8 and 0.4. This is just an arbitrary simulated data set. This could be a response time or some rating or whatever. And we assume that the standard deviation of the dependent variable is 0.2. And we assume that, so in all the presentations about contrasts, I will always use between subject designs. And you could say, okay, but we are doing linear mixed effect models because we are interested in repeated measures. And that's true. But yes, you can say that. So it's the fact that contrasts work exactly the same way in repeated measures and between subject design and within subject and between subject designs. So contrast generalized directly to within subject analyses. So everything we learn here about contrast can be used in linear mixed effects models as well. But it's more simple for us for the simulations to just and from other things. So it's simpler to just work with the between subject setup. So we assume 5 subjects per condition because we have 2 conditions. That's a total of 10 subjects. And we compute the means and standard errors for the dependent variable and use figures using create figures using ggplot2. So first, let's start with a very simple approach to simulate data. How would we go about that if we do it ourselves? I showed it briefly before, here to repeat. So I create a data frame where say I want to have 10 subjects, and then I have a factor x where with conditions x1 and x2, and each of these is repeated 5 times. So 5 times x1, 5 subjects are in condition x1, so 5 subjects are in condition f2. And then I set the seed of the random number generator. So if I run this again with the same seed, the random number generator will produce the exact same results. So I can replicate my analyses. And then I simulate data for the dependent variable y, and I just have the condition means here. So I say one condition has a mean of 0.8, the other one of 0.4, each of them 5 times, and then I add my residuals, my random noise. This is drawing random numbers from a normal distribution. We have 10 subjects, 10 residuals here with a mean of 2, and we said the standard deviation should be 0.2. And this gives us a data frame. We have 10 subjects here, 1 to 10, and we have a factor x with levels x2, and the first 5 subjects are x1, and the second 5 subjects are x2. And then for each subject, we have some observed dependent variable. And now let's compute a summary statistic. And this is now a tidyverse style. In tidyverse, you can take the data, have this pipe here that's called a pipe, the sequence of characters. We can group the data by x, so make 2 groups, x1 and x2, and then we can summarize the data with two summary functions. You can have the mean of y and a standard error of y by just having standard deviation divided by square root of n. And this gives us the summary table where we can see the means and the standard errors, but we can also plot that. Now this is a similar plot that we used before. You give the data, define the variables x. So now this summary table is our data. We have a factor x on the x-axis. The means we called this. The mean was called m. So the mean is on the y-axis, and then we have a minimum of y and a maximum of y, which is the mean minus the standard error and plus the standard error. And then we want to see points, want to see a line, and we'll see error bars. And this is what we get. We see, okay, here's approximately a mean of x1 has approximately a mean of 0.8, and x2 approximately a mean of 0.4. So this is a simple simulated data set. You can see, however, that the means here do not exactly correspond with the means that we have specified, and that's simply because of sampling noise. So of course we have a random sample of subjects, so this varies. For the comparisons that we make, it's easier actually to have very clear numbers where we know exactly what the difference is, and this can be implemented. So we will work with a function called it's a custom function that Reinhold Kliegel and Sven Hohnstein wrote in 2013, and it's called mixed design. And this can also be used to simulate data like that. And how does this function work? We first define a matrix of condition means. So again, we have here the 0.8 and the 0.4. And now different rows of this matrix, so this is a very simple matrix, it's actually just a vector. So in every, if you have between subject factor, every row in this matrix gives the mean for one factor level. What are the functions that you can? What are the arguments that you can specify in this mixed design matrix? It's the first argument is called B, and that's the number of between subject factors with n factor levels. So here we just have one factor, so we just have one number, and it has two factor levels, so the number is 2. No, I'm sorry. You could also have a situation where you have two factors, one with 3 factor levels and one with 4 factor levels. Then you would specify this as a vector 3, 4. Then you would have two between subject factors, one with 3 levels and one with 4 levels. And then you can also specify within subject factor, the within subject factors. And if you want to have within subject factors, we specify this as null because we don't have any within subject factors, but you can specify just the same way. If you have two within subject factors, one with 3 levels and one with 4 levels, you should just specify it as this list, as this vector of numbers. And then if you have within subject factors, you need to have different columns in this row. So every factor, every condition in the between subject design has to have one column in this vector. And then we specify M as the matrix of condition means, so the dimension must match the between and within conditions. So here we have no within subject factor, so we have just one column, and we have two condition between subject conditions, so two rows. And then we specify we want to have 5 subjects per condition, and we specify the residual standard deviation. And now comes an interesting argument, and this is called empirical true equals true. So if empirical equals false, then what happens is that the function draws random samples from the population with specified means and standard deviations. So you just, as if you would run an experiment where these are the true population means, and you just sample and you get sampling noise, and then this is exactly what we implemented on this previous page. Then the means vary around the true values in the simulated data. But you can also specify this is true, and what happens then is the sample means and the sample standard deviation correspond exactly to the specification. So that means that this is not a random sample anymore, and not a completely random sample from the population, but the mean of the sample, not of the population. The mean of the sample would be for x1 exactly 0.8 and for x2 exactly 0.4. And this makes it easier for the contrast analyses that we don't have to deal with so complex numbers. And long equals true just means that if you have long equals true, then one data point is one row. And if false, then one subject is one row. And we use in a between subject analysis, it doesn't matter. It turns out the same anyway. OK, so we can execute this code. So we simulate some data SimDat with the between subject design with two factor levels. Then we rename the factor and rename the factor levels to x and x1 and x2. And then we look at the data, we can see that we have this factor, this between subject factor, x1 and x2, each of them 5 subjects. Then we have here the subject variable, 10 subjects overall, and the dependent variable. Then again, we use tidyverse to compute summary statistics and create a ggplot with this command that I will So what is new here? I think what is new here is that I modify the scales a bit so that the whole scale is visible. But now you can see that the means, the condition means, the mean in each of the factor levels, here it's exactly 0.8, and here it's exactly 0.4. So this is the whole difference between the previous approach and this one, that the population means that we specified are exactly realized in the sample that we study, and that makes life a bit easier for the contrast analyses. Okay, now we have these 2 conditions and these 2 condition means, and I will discuss 4 different ways of how these condition means could be represented in a linear model, a simple linear model. That depending on how you specify the contrasts, you can have very different your coefficients, the intercept and the slope, measure very different things, test very different things in this context. And I will talk about the treatment contrast, the default approach, then changed baseline level, some contrast, and something we call effect coding. But let's look at it step by step. So treatment contrast, we learned in the previous section that treatment contrasts are the default in R. So if you specify a factor and you don't care about the contrast, you get a treatment contrast. So how does the treatment contrast describe this pattern of means? So what it does, the intercept B0 is just coded as the mean of x1, condition x1. So in this case, this would be 0.8. And so that's the baseline condition. That's what we learned in the last session already. And then the x2 would be coded as 1. And then the slope in the situation represents the difference between the x2, mean of x2 minus the mean of x1, x2 minus x1. And this difference would be 0.4 minus 0.8 is minus 0.4. And you can see in the background, I have here run a linear model with that setup, and we see that the intercept is 0.8, and the effect of factor x is minus 0.4. P-value is 0.013 here. So this is what R does implicitly. So the intercept then becomes the mean of the baseline condition. The reference condition. And the slope estimates the difference between the second factor level and the mean of the first factor level. However, we can also change the baseline. So what we can do in R, we'll show you later how to do that. We can say that x2 should be the baseline. Then the intercept would measure the mean of x2, which is 0.4. This is what the model does. And the slope would now measure the difference of x1 minus x2. So now we get a plus 0.4. So again, the difference, but coded in the other way. So this is just changing the baseline level, but using also a treatment contrast. And you already see that the intercept measures something completely different here. And the direction of the slope also changes. But the p-value of the slope actually stays the same. The t-value is 3.16, so that doesn't change. So as I said before, in this very simple example, maybe it's not so important which contrast you use. Probably all of the options would be okay because you could argue often we are not very interested in the intercept. We are mostly interested in the slope, and that turns out quite similar in these analyses. But I think it's important to know these different options before going to more complex setups. So one alternative option that we can use is the so-called sum contrast. So what does the sum contrast? How does the sum contrast work? In the sum contrast, the intercept measures the mean of all conditions. So condition x1 plus x2 divided by 2. So the mean of 0.8 and 0.4 is 0.6. And that's exactly what the model actually estimates. So the intercept is estimated as 0.6. That's the overall. That's called the grand mean. I abbreviate that as GM. And that's the mean of all condition means. So here the mean of two means, but if you have more factor levels, it's the mean across all condition means. And what is the slope estimating? The slope estimates the difference between the grand mean, B0, and the first factor level. So x1 minus B0, 0. And in this case, the grand mean is 0.6. This is 0.8, so the difference is 0.2. And we can see that this difference is directly estimated in the linear model. Interestingly, the t-value and the p-value remain exactly the same in this basic example. So here it doesn't matter much what we do. T-value is 3.16, p-value is 0.013 for the slope. However, the statistical test for the intercept, of course, changes. But again, in this very basic setup, it doesn't matter so much. In more complex analyses, these differences in the intercept can be important. And we'll come to that later. The next option that we have is so-called effect coding. And this is very similar to sum contrast. We again have the difference. The intercept again measures the grand mean. So that's just the average of x1 and x2, 0.6. We can see this in the estimate here. But the slope now measures the difference between both conditions again. So x1 minus x2. So the difference is 0.4. And the advantage of this effect coding, so this is if you just have a design with two factor levels, two-level factor, effect coding is nice because the effect that you see here, 0.4, the estimate for the condition reflects directly the difference between both conditions. So you can directly see from the statistical model output, okay, there's a difference on the dependent variable of 0.4 between x1 and x2. And again, the test statistics are exactly the same. Note, if you do the same in the sum contrast and you find this, you have to multiply it by 2. Not too difficult of an operation, but you have to say, okay, if I want to know the difference between x1 and x2 in this situation, you have to take 0.2 times 2 to know the difference between these two factor levels. Okay. So how does this work in terms of, and now I just gave you a conceptual introduction, what these different contrasts measure. Now let's look at how R does that. So the function, so if we have a factor in R, here x in SIMDAT is coded as a factor, we can apply this function contrasts, the contrast of the factor. And this function accesses the contrast coefficients for a factor. So what does it mean? So we said in the default setting in R, as a default setting in R, a factor is coded as a treatment contrast. When we so that's what we can see here in this contrast matrix. On the left side, we see the different conditions. Here we have x1 and x2. So in every contrast matrix, the rows indicate the different conditions of this factor. Here we have two conditions only, x1 and x2, so our contrast matrix has just 2 rows. And then a contrast matrix always has one column less than rows. So we have 2 rows and just 1 column. Because we just can test one difference here, one difference between x1 and x2. This is our contrast coefficient, our contrast for this difference. We can see that condition x1 is coded as 0, and condition x2 is coded as 1. That's exactly the same as what we had in the example with men and women. So men were coded as 0 and women were coded as 1. And how this coding takes place can be seen and accessed using this contrast function. So what does it mean for the linear regression equation? So if we want to predict the dependent variable in this linear model, it's very simple. We predict this based on an intercept and based on the slope times the predictor variable. And so x was the predictor variable. We said this can be a continuous variable. In this case, the contrast matrix tells us how what values are encoded in this x. So if we have x1, so for x1, we know that x is 0. This is what this contrast matrix tells us. So if we want to predict the mean value of the dependent variable in x1, we have to take beta 0 plus beta 1 times 0. Remember, x is 0. And this gives us beta 0. Right? So if we want to predict the mean of x1, this is just the intercept. This is what we can see in the figure. The mean of x1 is just the intercept, b0. So how about x2? If we want to make a prediction for x2, then we can see here x is 1, equal to 1. So the predicted condition mean for x2 is beta 0 plus beta 1 times x, and x is 1, so times 1. So this gives us beta 0 plus beta 1. So we can see if we take beta 0, that's 0.8, plus beta 1 minus 0.4 gives exactly 0.4. So you can see here that this regression equation directly works, and that these regression coefficients, yeah. So this is the default contrast, 0 and 1. And actually, when we run the model and say our dependent variable should be explained or by this factor x, what R does, it uses this contrast matrix to assign the x values, and then we can see that the estimates come out in the way that we have specified this. I have shown you before. So how can we turn this around? Now here I showed you how you can make predictions for beta for the condition means, but how can we define what the estimated regression coefficients, what they represent? So for x1, we said x equals 0. So to compute the condition mean, we have beta 1 is 0 plus beta 1 times 0. So the condition mean for x1 is beta 0. So we can turn this around and say beta 0 is just the condition. If we want to estimate beta 0, we can just take the condition mean of x1. But for x2, where x is equal to 1, we can see that the mean of x2 is the sum of these two. So we know that beta 0 is equal to the condition mean for x1, and then we can then we have an equation where only beta 1 is missing. So So this is just beta. The mean of x2 is equal to the mean of x1 plus beta 1. This is if we just replace beta 0 with the mean of x1. And now we can rearrange the terms and see that the intercept beta 0 is just the estimated mean for condition x1, and the slope is we can derive this from this formula. We just rearrange the terms. We take minus the mean of x1, so we have the slope is the mean of x2 minus the mean of x1. And now we can see this is something I told you a priori, that the intercept measures the mean of x1 and the slope measures the mean of the difference between the two conditions. But now here we have derived it from the regression equation. We can see that this is actually the case. So generally, it's useful to think of standardized regression coefficients as difference scores. They tell us how much the dependent variable y is expected to change when we increase the independent variable x by 1 unit. So we can, in this plot here, I've changed the x-axis labels. So here we say x1 was coded as 0, x2 was coded as 1. So if we change x by 1 step from 0 to 1, then the slope gives us the difference on the y-axis. So this is minus 0.4. Okay, so this is a difference score. How much does y change if we make an increase of 1 step on the x-axis? Okay, we can also set this default treatment contrast explicitly, so I'm going slowly, step by step. Maybe not so interesting for those who already know about contrasts, but just to make sure we have everyone on the table. So there's this contrast treatment function. Contrast treatment, you indicate the number of factor levels 2, and then you get exactly this contrast matrix that we saw before. So we can explicitly change the contrast settings of this factor by assigning the this matrix, contrast matrix that we get from treatment contrast to the contrast attribute of this factor. So we could also just say contrast of factor x equals to a vector with 0 and 1. This would give the same effect. So, and then if we estimate this model, of course, we get the same regression coefficients. But now with this formulation, we can also change the contrast here. We can enter a different contrast that we choose by ourselves because we want this to be the contrast that we use. Yeah, one thing for people who are knowledgeable of R, this is not new, but for some people it might be interesting to know. If we have this linear model where we just say the dependent variable is a function of our factor x here, what the model automatically does, it also estimates an intercept. So the intercept is this beta 0 is automatically added in R by adding a column of 1s in the design matrix. Okay, so yeah, so R automatically adds this +1. So you can also explicitly write was 1 plus, but you see that the output of the two models is identical. So R automatically adds this 1, and what this 1 does is just that it adds a column of 1s in the design matrix. And now let's look at how this looks like. So how does R arrive at these estimates? It implicitly uses the contrast coefficients to define a design matrix X of the linear model. We had seen the linear model is characterized by this equation y equals x beta plus epsilon. And now we can look at how what this X matrix looks like. And we can, in R, we can do that using this model matrix function. So model matrix, and we have to give it some data frame, and now we say we have this factor x, and this design matrix, what it looks like, it automatically adds this column of 1s here, and that makes sure that we get an estimate for the intercept, and then we have the second column, and that's our factor x2, and now we can see in this factor x2, it's not what R doesn't write x1 and x2 anymore. But instead of writing x1 and x2, it writes the contrast coefficients for each level. So x1 was coded as 0, we learned. So the first 5 values are coded as 0, and the second 5 values are x2. x2 was coded as 1, so we see the 1s here. So we can see that the factor levels are recoded into numerical covariates. And this is done according to the contrast matrix that is specified for that factor. And this is the design matrix X that R uses in the end for obtaining the estimates for the regression coefficients. So we can actually manually re-engineer that. So we now specify the model matrix, and we code these two variables that we see here, the intercept and the x1 and the x variable. We code this into new variables within our data frame. So if we look at our data frame, we now have here a variable called int. This is just a row of a vector of 1s. And we have this second variable C1, and that's now coding the contrast coding our conditions difference. So we don't have x1 and x2 anymore, but we have 0s and 1s here. Now what we can do, we can run the linear model again, and by typing -1 in the beginning, R knows that we don't want to have an intercept added automatically. Instead, we enter this intercept ourselves by taking this variable, and we specify C1 by specifying this variable. And when we look at the results of this model, we can see that the output is identical. Again, we have 0.8, that's the treatment contrast, the intercept, and -0.4, again, the t-values, p-values, everything is exactly the same. So this is what R automatically does if you have a factor and you have a contrast specified. It recodes that into the design matrix, and then you can use these predictor variables these numbers to predict the dependent variable. Okay, this will be important also later on for linear mixed effect models, because we will that's something we will do in linear mixed effect models, that we extract the model matrix and work with the continuous, so with the covariates themselves, rather than relying on this contrast function by the model, by R. So this will come back later on. Okay, so this is the basic. These are the basic mechanisms of how contrasts work. Let's try out different examples of contrasts. We had learned that I said before that we can set the baseline to x2, so that in the treatment contrast, not x1 is the baseline level, but x2 is the reference or the baseline level. And in that case, the intercept estimates the mean of x2, estimated mean of x2, and the slope estimates the difference between the estimated mean for x1 minus the estimated mean for x2. So the intercept estimates mean x2, and the b1 and the slope the difference between them. So how can we implement that in R? We can again use this contrast function, and there's an argument called base. We can say which is the base, what is the baseline level, and we just specify base equals 2. That tells R that now that now the condition 2 has a coding of 0. That's the baseline level. In fact, and x1 has is coded as 1. So now this is again the treatment contrast, but now the second condition is the condition 0, coded as 0. And if we specify that like this, so we set the contrast matrix with this new contrast matrix, and run the linear model again, then we automatically get here now different numbers. We get the 0.4 for the intercept and the 0.4 for the slope. How does this work in the linear regression equation? If we have y equals predicted y equals beta 0 plus beta 1 times x. So for condition x1, we have x equals 1. We can read this in the contrast matrix. For x1, the number is 1 for x. So we can predict y to be beta 0 plus beta 1 times 1, because x is 1. So to predict x1, the mean of x1, we have to take the intercept plus the slope, and this is easily visible. Intercept 0.4 plus the slope 0.4 gets us to the mean of x1, that's 0.8. But if we want to predict the data for x2, then x is 0. X is 0. So our prediction is beta 0 plus beta 1 times 0, and this just gives beta 0. So we can see that the intercept, that this just beta 0 gives us the mean, directly the mean of the x2 condition. Okay, so this is simply changing the baseline, and you can see that we can do that by applying this contrast function, matrix function contrast treatment, where we have a different contrast matrix, and then R automatically uses that in the analysis. So how about some contrasts? In some contrasts, the intercept we said before is the average of the two conditions, and the slope is the difference between the two conditions divided by 2. So how do we specify that in R? In some contrast can be obtained by this function contrast sum, brackets 2. Then a contrast matrix we obtain looks like that. The condition x1 has a 1, condition x2 has a -1. If we run that in our linear model, we get the estimates that we have plotted up here. We get a 0.6 for the intercept and 0.2 for the slope. And how does that work? How can we make predictions in this model? So now x1 has a value of +1. So if x is +1, then we can make a prediction that beta 0 for x1 is, if we want to predict the mean of x1, condition x1, we have to take the beta 0 plus beta 1 times plus 1, so x is plus 1, and this gives us beta 0 plus beta 1. And this is exactly what we can see here. Intercept 0.6 plus the slope is together to 0.8. And if we want to predict the data in x2, we have the x value of -1, x value of -1. So beta 0 plus beta 1 times -1 is beta 0 minus beta 1. So we can take beta 0, that's 0.6, minus 0.2, and we get to the mean of condition x2. Okay, so the sum contrast has this property that there's a 1 and a -1 in this very simple case. And we will see how this looks like in a setting with more factor levels later on. Effect coding, the intercept is again the same, the mean between the two conditions, but the slope is now the difference between the two estimates. Estimated means. Estimated mean for x2 minus x1, we said this is the whole difference and not just half the difference. So how does the contrast matrix for effect coding look like? We just take sum contrast divided by 2. Then we have here a 0.5 for x1 and a minus 0.5 for x2. If we run the model with this change contrast matrix, we see that the intercept is again 0.6, but the slope is now 0.4. So if we enter this in the regression equation, x1, we have a plus 0.5. So beta 0 plus beta 1 plus times plus 0.5 means that we have to compute the mean of x1, we have beta 0 plus 0.5 mal times beta 1, sorry. So we have beta 0 times the half of beta 1 to obtain a prediction for x1. And for x2, it's minus 0.5 minus 0.5. So we get beta 0 minus 0.5 times beta 1. So we have to take from beta 0, we get minus the half of 0.4 is 0.2. We get to this condition mean. So effect coding is just using a plus 0.5 and minus 0.5. Okay, yeah, that was a lot of detail. Sorry for going so slowly through all these steps. But I think it's important to get an overview of how this factor coding really works. Also for those who don't have any background on this yet. So as I said in this first section, I will just show you this different standard contrasts, and I will now do that for a new example where we have 4 factor levels. So far we had 2 factor levels, and in the 2 factor level case, all the slopes more or less tested the same thing. Just the estimates were slightly different, but the statistical test for the slope was always the same. This is now different when we change to a 4-level case. Again, we simulate data with a mixed design function. Now we have 4 between subject factors. So the matrix of condition means now has 4 values, 10, 20, 10, 40. And now that we specify that we have 1 between subject factor with 4 levels. The other things remain the same, 5 subjects per condition, standard deviation of 10 now. We rename the factor, compute the condition means, and plot them. And now we can see this is our data that we will work with. So x1 has a mean of 10, x2 a mean of 20, 10, and 40. And now the question is, if we analyze that with the linear model, we have the question is, what do our regression coefficients capture? So we are not in the case, we don't run an ANOVA and just test whether this effect is significant overall, but we are interested in specific comparisons. And now we will discuss in detail what kinds of comparisons can be done by using different contrasts. And I will again show you the treatment contrast, the sum contrast, but what is new is the Helmholtz contrast and the repeated sliding difference contrasts. I will walk you through these different contrasts and how they work. Or maybe before I talk all the time, were there any questions for the first part? I think it was rather quite straightforward. Or if there are any questions, please let me know. Okay, so let's go on. So how can we describe these condition means with numbers now? So what the treatment contrast does, it again defines the intercept, estimates the mean of the baseline condition, and now all the other effects coefficients test the difference of one condition to the baseline. So beta B1 estimates the difference between x1 and x2 and x1. B2 estimates how x3 differs from x1, and the last condition x4, the coefficient B3 again estimates the difference between this last condition mean and the baseline level. So every single condition mean is compared to the baseline level in the treatment contrast. So how does the contrast matrix look like in this case? So we can look at the contrast matrix again using this command, and R automatically applies the treatment contrast. So we can see that the contrast matrix has now 4 rows because we have 4 levels of our factor, and now we have 3 contrasts because 4 condition means yield 3 different contrasts that we can specify. And we can see that the baseline condition x1 is always coded with a 0. And the other conditions always have one column where they have a 1, and the other numbers are always 0. So how can we make predictions for the data? Now we have this linear model equation with several predictors. So if we say x1, then our x value, we can look this up in the contrast matrix, 0, 0, 0. So you have 3 zeros, and here for completeness, I add a 1 that's for the intercept. So in this case, we make a prediction for the data. It's just simply for the condition x1, it's simply the intercept beta 0. So that's what this 1 indicates, that we just have the intercept. But all the other slopes, so x1, x2, and x3. So there's in this equation, there's an implicit 1 before this beta 0. We can think of this. There's a 1 times beta 0. Okay, how do we make prediction for x2? Now for x2, we see that we have the intercept, but also x1. There's this first contrast. For this first contrast, there's a coefficient of 1 intercept, and then 1, 1, 0, 0. So what this turns out, if x1 is 1, the other ones are 0. So then we end up with beta 0 plus beta 1. To compute the mean of x2, we have beta 0 plus beta 1. For x3, it's the same. Now the next, the 1 is at the next location, in the next contrast, so we get beta 0 plus beta 2. And for the last condition to predict x4, the mean, we have beta 0 plus beta 3. Okay, so this is how we can translate this contrast matrix into predictions for individual condition means. And if we use this contrast matrix to estimate a model, we can see that our coefficients that we estimate directly correspond to the numbers that we have specified in our figure. So the intercept, the estimate is 10. This is exactly the 10 that we see in the figure. The first contrast for x2 is again 10, and this is exactly this difference between 20 and 10 that we see here. Then the next contrast is estimated as 0, because x3 is equal to x1. And the last contrast estimated as 30. That's the difference between 40 and 10. So that's exactly this contrast that this estimate that we see here. Okay, so you can see in the case where you have more factor levels, the treatment contrast compares each factor level to the baseline using this contrast matrix here. So how about the sum contrast? What does the sum contrast test? In the sum contrast, the intercept captures the grand mean. So x1, x2 plus x2 plus x3 plus x4 divided by 4. We can see that the mean of these 4 numbers here is exactly 20. So the intercept captures this grand mean, so mean of all condition means. And then the slopes capture the difference between each factor level and the grand mean. So the slope B1 captures the difference between x1 and the grand mean and the intercept. B2 captures the difference between x2 and the intercept, and B3 captures the difference between x3 and the intercept. And x4 is not explicitly modeled. We will see how the model can still make predictions for x4, because the model can still do that. So how does the contrast matrix for the sum contrast look like? We can see that in the sum contrast, there's again our four rows for our four factor levels. We can see that the last factor level, x4, has always has a value of -1 in all of these contrasts. So each of the columns is one contrast. And then there's a 1 on the diagonal here. In the first contrast, the first condition is coded as 1, and the second is coded as 1, the third contrast, the third condition is coded as 1. If we go back to our regression equation here, so beta, the predicted data as a function of the beta of the intercept, the slope times x1, slope 2 times x2, slope 3 times x3. We can again make predictions for the dependent variable. So if we have x1, we want to make predictions for x1. Now we can see for x1, we have again the intercept, and we have this first number 1, but then 0, 0, 1, 0, 0. So this gives us, for the prediction, we have to take the intercept plus x1. This is what this 1 here indicates, plus x1. So the intercept plus x1. And the same result occurs for the other conditions, x2. We have the intercept, and then we can see here the contrast x, the values for x are 0, 1, 0, 0, 1, 0. So x1 falls out, x3 falls out, and beta 2 remains. So to obtain the mean of x2, we have to compute beta 0 plus beta plus b2. So beta 0 plus b2 gives us exactly this value of 20. And with the third row, our value for x is 0, 0, 1. So the intercept, and then 0, 0, 1. So now this gives us the intercept plus beta 3, and that's how we obtain the estimate for our next factor level. And now we come to the last factor level, and here all the x values are -1. So if we want to make a prediction for x2 for x4, we have the intercept, but then we have -1, -1, -1. So if we enter this in this regression equation, we get the intercept beta 0 minus beta 1 minus beta 2 minus beta 3. And interestingly, this exactly gives us the estimate that we want. So beta 0 is 20 minus beta 1. Beta 1 is -10, so minus and minus cancels out, plus 10. Beta 2 is 0. So this doesn't change things. Minus beta 3. Beta 3 is -10. So again, a plus 10. So 20 plus 10 plus 10 gives us exactly the value of 40. Okay, so interestingly, these -1s allow us to use the other contrast coefficients to make a prediction for the last factor level. And if we now run the model, we have specified that the sum contrast should be applied to the factor. If we run the model, we see that now we get very different coefficients compared to the treatment contrast. So now the intercept captures our effect of 20. X1 gets us the -10 here, x2 the 0, and x3 gives us the -10. So if we would not know what the contrast matrix is, so note that these numbers are completely different from the treatment contrast, right? They're just testing different hypotheses. So all of these are legitimate hypotheses. The question is which hypothesis applies to our data? Which is the hypothesis that we are interested in? So the sum contrast would always compare each condition mean to the grand mean. The treatment contrast would compare each condition mean to a baseline condition. So if we don't know this, then these contrast coefficients that we get here are completely meaningless. And also the statistical tests that we obtain are completely meaningless because we don't know what they represent or what comparison they encode. Okay, let's go to Helmholtz contrasts. There's a lot of stuff here now if you're new to this. But for others, others might already know all of this. So yeah, I'm not sure. So how does Helmholtz contrasts? How do Helmholtz contrasts work? In Helmholtz contrasts, the intercept is again the grand mean, the mean across all factor levels. So this is 20 here. And the first regression coefficient in Helmholtz contrast tests the difference between x2 minus x1. So the difference between these two conditions. Then the second contrast in Helmholtz contrast takes the average of these two, x1 plus x2 divided by 2, and compares the average, so that's 15, average of x1 and x2 is exactly 15, and then compares this average to the third factor level. So x3 minus the average of the first two. And 15 minus 10 is exactly, the difference is exactly minus 5. So how is what is the third regression coefficient code? So now we take the average of the first three factor levels, x1 plus x2 plus x3 divided by 3, that's roughly 13. And now we compute the difference between this mean and the last factor level. So x4 compared to the mean of the other three. So this is how what Helmholtz contrasts tests in principle. So we can obtain the contrast matrix for Helmholtz contrasts here, 4 factor levels. And the contrast matrix looks like that. The standard Helmholtz contrast. The first contrast codes -1 and 1 here. So it's a comparison of x1 versus x2. The second contrast compares x1 and x2 against x3. So -1, -1, and +2. And the last contrast codes the comparison of the first three conditions against the last, -1, -1, -1, and 3, +3. So now we run this model again, but now we see so that things don't work out as we expect them. So the intercept measures the mean of 20, that works out, but the slope for x1 for the first contrast is actually 5, but it should be 10 here. So this is only half of what we want to estimate. The slope for x2 is -1.667. That's 1/3 of 5. So it's 5 divided by 3. And the last slope here is 6.667. That's actually 26 divided by 4. So we see that these coefficients don't work out. However, it turns out that the Helmholtz contrast, these p-values actually, so the contrast coefficients are scaled versions of these differences that we see here. They are not directly the difference scores, but this is half the difference, 1/3 of the difference, and 1/4 of the difference that we are interested in. So for the p-values and the t-values, that doesn't make a difference. But the estimates, which should be of interest to us because they tell us how much these differences are, they are kind of scaled to compared to what we are really interested in. And I will show you a way to create a better Helmholtz contrast in the next session, where these differences reflect, where these coefficients estimate directly the differences that we want to estimate. But it's important to note the Helmholtz contrast first compares the first two conditions, then the average of the first to the next, the average of the first three to the next, and so forth. That's the important thing to note. And for the standard Helmholtz contrast, these estimates are scaled estimates of the differences that we observe. Okay, so last contrast for the session, that's repeated or sliding difference contrast, or a simple difference contrast is also a name. So how does that work? The simple difference, the repeated contrast always compares to neighboring factor levels. So the first contrast, so the grand mean, the intercept is again the grand mean. And now beta 1 captures the difference between the first two levels. Beta 2, the difference between the next two levels. So the first one is +10, then -10, and then the difference between the last two levels, that's +30. So how does the contrast matrix for simple difference contrast look like? can have this function contrast simple difference. And we can see that this contrast matrix looks quite complicated. So minus 0.75, minus 0.5, minus 0.2, 0.25. So yeah, this is a rather complicated, not very intuitive way to, so it's not entirely clear from this contrast matrix what is actually tested. But when we run the model and estimate the coefficients, we can actually see that the intercept is 20, that's the grand mean. The first slope is plus 10, as we saw up here. The second slope is minus 10. That's exactly the minus 10 we see here. And the 30 is the difference between the last two conditions. So yeah, so this contrast always tests differences between neighboring factor levels. That's, some people argue that this is a very useful contrast in psychology. Yeah, these were the different contrasts that I wanted to introduce to you to show you what kind of the state of the art is with contrasts. The state of the art with contrasts, or not the old state of the art with the contrast was, that's what many people did at least, was to decide, to know what these different contrasts test, which hypotheses they test. And then when you have a study, you simply decide which of the contrasts you use, because one of these contrasts most closely maybe represents the hypothesis that you have in mind that you want to test in your data. Okay, that's actually as much as I wanted to tell you in the session. The next session, so one question that can come up, of course, so these are a lot of different possibilities that we see here. So sorry for going through all these details with you, but I think when you want to code contrasts in a complex design, you need to know these different ways and how this can be done. Sorry for those who already knew it. But the next step will be that if we can ask the question, sometimes we might have hypotheses that are not well represented by any of these contrasts. So what do we do then? And in the next session, I will show you a way how we can still create a contrast matrix, even if the default contrasts don't work for us. So I will show you a procedure and also an R package of how this can be done.